AP Cactus AB, Unit 10, Day 2. We're going to now officially start doing some volume problems. I'm going to start with volume by cross-section. And I think this method is a little more direct than the next one that we'll be doing. But we have solids are three-dimensional figures, and we're going to use this if they have a similar cross-section. So there's some sort of like shape that every slice has. So area could just be generic for that. You kind of think of like, a stack of like CDs or something. Discs. We could do that, and keep, cutting it. And the volume, the cross sections in this problem, cross sections are congruent. They're all the same size, which is generally not true, but in this case, you can say it is. The volume of one slice would be the area, circle, pi r squared, and then times the height of that slice. And so this is area. This is two-dimensional. This is going to be like dx or dy, the thickness of the slice, and that's one-dimensional. So if you multiply 2 dimensions by 1 dimensions, you will get 3 dimensions. So that kind of makes sense. Just that it will give you volume. In this case right here, we have a cone, and the slices are all circles, but they are changing size. Okay, so that's going to be a little more common. Cross sections are not the same, but they are similar, meaning they are smaller and bigger versions of each other, like similar triangles or whatever. Now, these are some of the typical cross sections on the AP test. They could be squares, equal sides. Each side is S. They could be rectangles, two opposite sides that are congruent. Now, usually with the rectangles, they're going to tell you that the height is like 3 times the base or something like that. Do half of a circle. You could do full circles. That isn't as common. You do half circle. You do like equilateral triangle, and that's the formula for equilateral triangle, which you could also kind of rederive pretty quickly because it has equal angles and they're all 60, which means this top one up here gets split into 30, 60, 90. And so if this is a side, this is going to be half of a side, and this is going to be half of a side times the square root of 3. And so if you multiply base times height, base is S, the height is 1/2 S root 3, you get root 3 over 4 side squared. So let's see. There could also be like combinations of shapes, like a square minus half of a circle, take it out. Now, the challenge here is that you want to get everything in terms of one variable. So you could say, well, let's replace the r's with 1/2 s, or you could replace the s's with 2r, whatever would be more convenient. You could do something like an equilateral triangle with half of a circle on top, or a square with a half of a circle on top, or a square with an equilateral triangle on top. There's just giving you some different ideas. Now, the game plan, what's our strategy here? Okay, we're going to go into this on the back, but we want to sketch kind of the shape with at least one slice, sketch one slice on it, and then use the coordinates of that slice to help you write your formula for the area of one slice, and then integrate it. So let's try a couple examples on the back. So we'll start with the free response problem all the way back from 1996, which was the year I took the Calc AB exam. Got a 5. I don't know if that gives you any more confidence. But this must have been a problem I did. One of the 6 free response problems. So let R be the region in the first quadrant. Now, they may give you a picture. They may not. You might have to draw the picture yourself. I've already kind of drawn it here. And I've kind of drawn it slanted the page to kind of give it a little more perspective. I'm usually not going to probably draw the axes slanted like this, but I just did here. So you have y equals 1 over the square root of x. We're going from 4 to 9. It says, find a volume of solid whose base is region R and whose cross sections are perpendicular to the x-axis. So they're going to tell you the direction of the slices. So the cross sections are perpendicular to the x-axis. That means they're vertical slices. Okay, and they're going to tell you what kind of shape they are too. So they're going to tell you. You're not going to have to guess. They're going to be square. So I would draw one slice here, and I kind of make it stand out in addition to my drawing. So that's one slice, and it has a thickness to it. We're going along the x. It's at some generic coordinate, x coordinate. It's tied to this curve here that has an x, y coordinate. That's probably going to, affect the size of the square as you move along. So we could draw some other slices. I usually wouldn't do this, but, right now it might kind of help you understand what we're doing. But, so it's sort of like, it looks kind of like a, skate ramp or something. So we sketch it, we sketch the graph, the base area, we sketch one slice, perpendicular to the x-axis in this case. Sometimes they're going to be perpendicular to the y-axis though. They're going to tell you. This is sort of our general formula, right? Some area. And then I might even do this. I like to do this sometimes, draw a picture of the type of area that each slice has, like a little square, put the generic formula for it. Now, S, the sides of the square, somehow have to be in terms of x or y. And so on these ones right here, the side of the square is the y coordinate of the curve. So we could write that. We say, well, it's going to be y squared, which it is. We can't integrate y squared with respect to x. So we need to get it into terms of x. Okay, so get into terms of x, since we want to integrate with respect to x in the x direction. So that's pretty easy. It's 1 over the square root of x, right, squared. And then we could simplify it. It's going to be 1 over x. And so that's just the setup. I mean, that's the hard part, because after that, you're going to be doing work that we've been doing a lot of definite integrals. So this is going to be natural log of the absolute value of x, 4 to 9. We get natural log of 9 minus natural log of 4. Might simplify it, combine it together. If it's multiple choice, a lot of times they're probably going to ask you to do that. I mean, this is acceptable in free response. And then on our calculator, if you wanted to get a decimal, it would be natural log of 9/4. So it'd be 0.810 or 0.811. Round or truncate. I'm a fan of truncating. It's hard to mess up. So here's the thing too, like on tonight's homework, you're going to be doing a lot of these by hand. I'm going to let you start using your calculator, but you also could use your calculator to check your answers real quick, the ones you have to do by hand, especially on a worksheet, you know what I mean? So we could do this. I wouldn't bother entering this into the Y menu because I don't really want to graph it. I'm going to just plug this into my calculator. So I'm going to say math 9. Right, and I'm going to say 1 over x, comma 4, comma 9. And sure enough, we got it. So usually I'm going to do math 9, f and ends, right? And then I'm going to put, That brings you to the home screen. And put the function 1 over x, and then integrate with respect to x, and then 4, then 9. Some of you guys have, some of yours actually show the notation that's like what we're doing here, and you have to fill in all of these spots. So this is where the 1 over x goes. That's the function trying to integrate. This is where the x goes that we're integrating with respect to x, and this is the 4, and this is the 9. So you can use that to check answers. I'm also going to let you probably just do that on some of the assignments coming up. Okay, so here's another one that's a little tougher. So let R be the region bounded by y equals x squared, which is a parabola, and y equals the square root of x, which is the top half of a sideways parabola, x equals 0 and x equals 1. So this is the base region that we're going to build off of, okay? And the shapes are going to be semicircles. And the cross sections are perpendicular to the x-axis, so they are vertical slices. And I would just do one slice and draw it on here. Okay, so you really should draw pictures of these. And, you know, you could draw more slices. They're all gonna, you know, it's gonna kind of look like a upside down canoe or something. But it's really one slice I really want to get there. Now, it's at some location x. So every slice has some area, which are going to be half circles, which is going to be 1/2 pi r squared. We're going from 0 to 1 in the x direction. Now the radius of this is this, or it's this. But what we could do is we could figure out, well, this whole thing right here is the diameter. And the diameter is y top minus y bottom. It's the distance between the top curve and the bottom curve, right? Y top minus y bottom. So I mean, we could do that, y top minus y bottom, but then we got divided by 2. Now I can move the pi over 2 out in front. That was already there, but I got to divide this by 2, and it has to get squared. That's one of the mistakes people make a lot. It gets squared, becomes a 4. You could bring it out in front and be pi over 8. Okay, not pi over 4 though, pi over 8. The divided by 2 has to get squared. Now y top is the square root of x minus y bottom is x squared. But then it's going to get squared, right? So to integrate this, I think your best choice is to go ahead and FOIL this out. So it's going to be pi over 8, 0 to 1. This is x to the 1/2, so it's going to be x to the, it's going to be x. And this is, you know, if it helps, you can write it out. So we're foiling this. So this is going to be minus x to the, you add the exponents, rules of exponents. It's 2.5, it's 5 halves, minus x to the 5 halves, plus x to the 4th dx, right? And so that's going to be minus 2x to the 5 halves when you combine those together. So the antiderivative is going to be x squared over 2 minus 2x to the 7 halves divided by the new exponent, multiplied by the reciprocal, plus x to the 5th over 5, 0 to 1. And so we're going to plug 1 into this. It's going to be 1/2 minus 4/7 plus 1/5. And then if you plug 0 in, it happens to be 0 this time, but always be careful. Sometimes you plug 0 in and you get some numbers out still. Now, least common denominator would be 70. So 14, 35. So we get 35 minus 4 is 31. I'm sorry, 35 minus 40 is -5, plus 14 is 9. So it's going to be 9 over 70. So it's going to be 9 pi over 560. On your calculator, the decimal is going to be 0.050, which is really small, right? But you can imagine this is all fitting into one unit, 1 cubic unit. This is a tiny piece of it. Now, of course, we could do this on our calculator, which is, as soon as you're allowed to, might as well do it on your calculator. So I do math 9, and you could put the pi rate inside, or you could keep it outside. I might put it in front. You can put stuff in front. And then it's going to be, but if you do it on your calculator, I wouldn't bother with all the foiling. It's going to be square root of x minus x squared, close, comma x, comma 0, comma 1, and this should do it. Nope, something's wrong. Oh, I forgot this squared, which is a super common mistake. People just forget to write it, or they write it and they forget to type it in there. So I'm going to go back in here and say second insert squared. That should do it. There we go. 0.50. Round truncated comes out the same this time. Okay, so that's what we're going to be trying on today's assignment, which is a worksheet. And all of the cross sections on today's worksheet will be vertical cross sections, so you don't have to worry about any horizontal slicing yet. I haven't showed you guys how to do those yet anyways. So, and nicely conveniently, these graphs are already drawn for you. So you should just draw one slice to help you set it up. And then you are allowed to use a graphing calculator today. If you'd like practice, you could try and do them by hand, which I will do. So, I don't know. But there you go. If you want some practice with the details, then you can work them out by hand also. But you definitely want to get good at doing them on a graphing calculator. All right, that's it.